Hello, my name is Jose, and I'll be working on problem number 10 from homework number 2. So here's number 10. Standing waves on a 1 meter long string that is fixed at both ends are seen at successive frequencies of 36 Hz and 48 Hz. And there's two parts, there's A and B. So for A, it's what are the fundamental frequency and the wave speed? And for B, draw the standing wave pattern when the string oscillates at 48 Hz. So from the given information, what we do know is that the length of the string is equal to 1.0 meters, and we are seeing two frequencies at 36 and 48 Hertz. So we could assume that f of m is 36 Hertz because it's some nth harmonic, and we know that 48 Hertz is bigger than 36, so we could say that that's some f of m plus 1. And then we're looking for the fundamental frequency, and we know to find the fundamental frequency, you would have to use this equation here, where m is just some integer, just all the way to some nth number. And we know that the speed of a string is equal to this equation here, and it's based on tension and linear mass density. So we know that the speed of a string is not dependent on the frequency or the wavelengths per se. It's mostly based off of this equation here. So what we're trying to find are the fundamental frequency, so f of 1 basically. That's the fundamental frequency, because the fundamental frequency is basically where m equals 1. So we don't know what that is. And we're also looking for the wave speed of the string. So we don't know those two things. What we do have are the two frequencies that are given. And what we do know is that in order to get the fundamental frequency, we can subtract these two. The difference between these two will give the fundamental frequency. Because the fundamental frequency, when you subtract these two, you will get the difference between them. Because if you actually do this math right here, m plus 1, like that, minus m, and then it's going to be equal to 1. So you can see here, you get this right here. So that's how that math happens. So if you want to do this in terms of the frequency, so it'd be f of 1 is equal to f of m plus 1 minus f of m. I literally just use the subscripts over here to show. So if we plug in these values here, if we plug in these values up here, we get f of 1 is equal to 48 Hertz minus 36 Hertz. And when we subtract the two, we get 12 Hertz. So we know that the fundamental frequency is equal to 12 Hertz. Now the next step is the wave speed. And well, in order to find that, we could use the fundamental frequency that we calculated and plug it into this equation up here. So let me just do that. So f of 1 is equal to mv over 2l. And since we're looking for the wave speed, which is right here, we're going to rearrange this equation here to find the wave speed. And once we do that and rearrange everything, we're going to get that the wave speed is equal to f of 1 times 2l. Since the m right here is m equals 1, so we just can, we multiply this part right here by 1, so that's where the m goes to. And we're given the length up here, and we already calculated the fundamental frequency, so all we're just going to do is a plug and play. So the wave speed of a string is equal to 12 Hertz times 2 times 1 meter. And once we calculate just 12 times 1, or the 12 times 2 times 1, we're going to get 24 meters per second. And we know that we'd want the units to be meters per second. This is reciprocal seconds. That's what Hertz is basically means. and we have meters, so that's how we got these units right here. So we know the wave speed as the wave propagates along the string is 24 meters per second. So we just calculated A. Now we're going to do part B, which is we're going to draw the standing wave pattern when the string oscillates at 48 hertz. So for B, what we do know for part B is that we're given the frequency. So if we turn back to B, we're given a frequency when the string oscillates at 48 hertz. So we want to know the mode, or the M, which is this integer right here. Like we're trying to calculate this with this frequency. So I'm going to just write out this in the back. So f of some nth harmonic, we don't know yet, that's what we're trying to calculate, is equal to 48 hertz. And we're given that the length is 1.0 meters. And we do know that the formula for a frequency when both ends are tied is the frequency at some nth harmonic times 2 times the length divided by the wave speed of the string. And well, we already found out we're already given the hertz, we're given the length, and we calculated the wave speed of a string over here on this side right here. And the wave speed of a string is always constant in terms of standing waves, since as we set up here, the speed of a string is dependent on the tension and the linear mass density. And for this problem, for number 10, we just assume that the circumstances like from tension and linear mass density are kept constant. So therefore, the wave speed could be considered constant. So we could use that the wave speed of a string is equal to 24 meters per second. So we're given basically every component, and so all we have to do now is rearrange this equation. Oh, I made a small mistake here. This is actually M. So it's the fundamental frequency, or not the fundamental frequency, the frequency at some nth harmonic is equal to M times 2 times the length over the wave speed. And we don't know what M is, so M is equal to some unknown number. But we do know this, which is up here. So now we're just going to rearrange this equation, which I'm going to do down here, so we could find the mode. So we get, when we rearrange everything, the frequency times 2 times the length over wave speed. And so at this point we just do a plug and play. So 48 hertz for the frequency, 2 times the length, which is meters right here, over the wave speed, which is 24 meters per second. And once we calculate this in a calculator, we get that M is equal to 4. And what we do know is that this, for standing waves, that when the standing waves are fixed at both ends, what we do know is that there's going to be a series of nodes and antinodes. And antinodes, they correspond with places of constructive interference, and to be particular, in this case, it would be max constructive interference. And then for nodes, it'll be places of perfect destructive interference. So we know that M equals 4. So we could assume that in this case for standing waves, that every time for each, like for the mode, if M equals 4, we could assume that there's going to be 4 antinodes. So it's like a direct correlation between the actual like integer for mode and antinodes. And what we also do know, I'm going to draw a diagram right here. So we'll just pretend this is some wall. and this is another wall. Okay. And this is going to be the x-axis. And I guess I'm not going to draw it over here. We're just going to assume this wall right here is going to be like the y-axis. And the y-axis would measure displacement, and then the x-axis is just the string propagating along the axis. So let's just say the string would be going like over this way at some wave speed. Let's say like there's a person here doing just putting energy on the string, and the wave is just propagating along, and it's gonna hit this hard end, reflect, and as the person who's adding more waves onto the string keeps on doing that, and as it keeps hitting the wall on reflection, it's gonna keep oscillating and oscillating till the point where you're gonna see nodes and antinodes. That's how these standing waves work. And we know that m equals 4. And another thing that we do know is that each end, for it's a definition for like each end, there's gonna be there's gonna be nodes at each end. So we know that there's gonna be a node here and a node over here. So we know that's how it's gonna look like at these ends. And we do know that there's gonna be 4 antinodes. So it's gonna be 1, 2, 3, and 4. And standing waves go up and down. So we're just going to draw the reverse of that. And so this is our diagram for when m equals 4 for standing waves. So as we see here, these are areas of max constructive interference. And then these areas right here is perfect destructive interference. Yeah, so we just calculated for number 10.